So you capture price. Good. Hi everyone, welcome to Google Cambridge. It's a pleasure to have you here. And I want to give, first of all, a big thank you to Eila, who hosts this meetup and who invited us to this session. So for today, we're going to have two talks. One, it's going to be by Robert Bradshaw, who is also a Googler. And the second one is going to be by Eila. So my name is Grace Cuevas. I am an open source strategist for Google Cloud. I work in open source projects, and the specific project I work with is Apache Beam. So we're going to be talking about it. Well, Robert's going to be talking about it a little more in detail. So I just want to say welcome, and I wanted to kick it off. Eila, do you want to introduce yourself, or do I want to start your talk?
Sure, the slides are here. I see the camera. I'm going to start recording. But the slides are here.
Yeah.
Let's stop recording.
Let's see.
Our presenter camera. Excellent.
Okay. So now we have the slides as well. Okay. So I would like to welcome Robert to the stage, and I'm gonna let him introduce himself and also the talk. Thank you.
Okay, so I'm Robert Bradshaw, and I'm going to be talking about Apache Beam and machine learning. And so I'm actually not, surprisingly, a machine learning guy. I deal with mostly with big data processing. I've done a lot of parallel processing. Been working most of the decade at Google doing parallel processing. Also, I have a lot of personal experience with parallel processing, being a father of twins, twice actually. So parallel processing runs in the blood. So. Well, why am I here then if I'm talking about doing things in parallel? Well, yes, this is parallel. So the thing is, when you're doing machine learning, especially in production, lots of times you have this core machine learning that you care about. You're discovering new algorithms and ways to arrange things, and you have this nugget, which is machine learning. But usually you have to deal with so much more than just the machine learning to get this into production. You have to deal with configuration. You have to deal with getting your data in. I guess this. Okay, the gray in this slide, imagine this gray box around here, and unfortunately I think I use this gray a lot. So you have to learn about how to handle this data, how to get your data, to clean it up, to process it. When you have your models, you have to say, okay, how am I going to evaluate whether my model's good or not? I have to serve it, probably at scale. I have to orchestrate all this stuff. And so this is a big burden when really the thing you care about is this little nugget, machine learning code. That's the cool part of your algorithm. But for production, to make this useful to anyone else, you have to do all this other stuff. And so in this talk, I'm going to talk a little bit about Apache Beam, which, being data processing, actually handles a lot of these boxes around here, which are really data processing problems. Then I'm going to introduce TensorFlow Extended. This is something that we've used internally at Google that we're in the process of open sourcing. So there's TensorFlow Transform and TensorFlow Model Analysis. And I'm going to talk a little bit about some of our future plans there. And then, time pending, I'm going to do a little bit of a demo. So Apache Beam, what is Apache Beam? Well, it's a system for defining and executing data parallel pipelines. And so this means that you have a bunch of data and you want to process it, and it's too big to fit on one machine. So why do you need this? Well, as I heard some people talking about earlier, when you do machine learning, the critical thing is the input is data. You need data. And if you don't have enough data, you're just not going to have very much luck. So you need a lot of data. And the thing is, the more data, the better. But then you have a problem with the more data, the better. Your data gets really, really big. And so now you have a problem of how do you handle this data? And in fact, sometimes your data is not just really big. Maybe it's infinitely big. So you have people clicking on your web pages, playing on their mobile phones, and you want to be able to ingest this data in real time, hopefully keep up with it at least, and do something useful with it. But you're not going to have your one little laptop being able to do this. So kind of the first thing that one of the first breakthroughs in being able to process big data was this idea of MapReduce. So it's a really simple concept where you have a map operation that takes in data and does some transformations to it. And then you have this reduction operation that takes So when you transform your data, you assign keys to it, and you shuffle by key. So you kind of group things that are supposed to go together. And then you have this reduce operation that then clumps the like things together and processes them in a whole and spits out some output. And by now, this seems like an obvious concept, but back in the day, this was a really big step forward, because now when you think about parallel processing, you no longer have to think about, okay, I need to somehow allocate 100 machines. I need to worry about getting the data to the machines in the right order, and what if some of my machines die on me? How do I take that up and reprocess it and avoid duplicates and all that kind of stuff? This kind of is a framework that gives you the ability to say, I'm going to focus on my logic. I'm going to focus on a map operation and a reduce operation, and then the underlying infrastructure, the framework, will take care of all the messy details, like how to actually farm out the computation to a set of machines in a fail-safe way, in a robust way, such that I can just focus on my logic. And of course, MapReduce kind of wasn't the be-all, end-all of it. It was kind of the start of things. When I started at Google, we were working on something called Flume. At the time, it was called Flume Java. Now it's multi-language. And it kind of was another step beyond MapReduce, where you say, we don't just have one map and shuffle and reduce operation. Our pipelines are really these DAGs, where you have possibly multiple inputs, and you're joining them, you're filtering them, and you're processing them. You have multiple outputs going on. And so it introduces kind of a higher level abstraction on top of MapReduce to really create entire pipelines that are then orchestrated by the Flume system. And originally, this was compiled down to a series of MapReduces. And now we kind of have our own execution engine, so it operates these DAGs natively. So of course, we didn't stop there. So since the MapReduce paper was published, at Google, we've done a lot of things. We had Flume, we had Millwheel, we had PubSub, we had Spanner, Bigtable, a whole bunch of technologies that we developed. And occasionally, we'd publish a paper on them. At the same time, externally, people said, oh, this is a really good idea. I'm going to write something. So we had Hadoop, we had Spark and Crunch, and Tez, and a whole bunch of other things that developed. And then over the last 10 years, we've looked at this, and we've kind of got two ecosystems. At least from Google's perspective, we have all the tools that we developed for our needs, and then we have all the tools that other people developed that embody the same concepts, but are just incompatible enough due to arbitrary choices that were made that you can't just seamlessly switch from one to the other. You can't just say, oh, I have this pipeline that runs externally, now I'm going to run it internally. That doesn't quite work, because arbitrary choices were made in the APIs, innovations were made in the interfaces, and so on. And so what we developed, and this was in 2014, is something called Google Cloud Data Flow. We said, okay, this is something that we're going to use internally. It's kind of the evolution of Flume, but we're also going to offer it externally, so that people who do data processing don't have to kind of span these two APIs. You can just do the same thing. And we published that in 2014. We got some users of it. And then we decided, well, not only are we going to offer the service available externally, let's go all the way. And we joined together with a couple other companies and created Apache Beam. So Apache Beam is actually an open source product to do data processing. And it's one product that we can use, kind of, it spans boundaries. And I'll show you that it spans the boundaries in other ways too. So Apache Beam was released as an Apache project, well, as incubating Apache project in the beginning of 2016. And then we did a lot of development on it and graduated as a full-fledged Apache project at the end of 2016. And then since then, we've kind of continued to grow and develop this data processing platform. So what exactly is Beam? So Beam isn't just like a piece of software like, you might have MapReduce or Spark. Beam is really a portability framework that allows you to process pipelines. It allows you to write a pipeline in one way and then execute it on a variety of backends. And then you also want multiplexing the other direction, where you want to be able to write your pipeline in multiple different ways and execute it on multiple different backends. So for instance, some people are more familiar with Java, other people prefer Python or Go or R. And it's not, one of the things we discovered, it's not necessarily always the language, but you really want to be able to offer the environment and the ecosystem that these different tools have around what people are comfortable with. But then at the same time, you want them to be able to execute on the different backends. So you take your language of choice, like say Python, and you write your pipeline. Then you say, now I want to go and execute this thing. And we can execute it on a local runner. That's the first option when you're doing development. And you just say, okay, it's just going to run on my one CPU. It's going to churn through the data in the naive way, spit out the results. And that's great. And then you say, okay, now I want to do it with more data. And what you can do is you can just take the same code and swap out the runner. And so you can say, I have a Spark cluster. I want to now go run that on a Spark cluster. Or I want to run it, I don't only really want to care about managing my own machines. I'm going to go and run it on Google Data Flow. And then I just submit my job there, and it does the data parallel stuff. And we also have a Flink backend. There's a gear pump backend. There's a someone recently introduced I think it's called SMAMSA backend. Anyway, so there's a lot of people that are developing these backends that you can plug into Dataflow, and that way you can take your same pipeline and run it in the different environments. I have to admit this picture is a little bit of an ideal situation. We're still working on making exactly all of these backends talk to each other, but we're getting really close. Today I was, for instance, running a Beam Python pipeline on the Apache Flink, which is written in Java, and then it calls back to Beam Python. So this is kind of what the vision of Beam is. This helps with a lot of other things. For instance, it's really nice to be able to write unit tests of the actual code that you're running. You just write a pipeline. You just provide it with a small amount of data, verify the small amount of data that came out is the right thing, and now you can unit test exactly the same code that you're running in production. You don't have this problem where you try out your things, you get a working program, then say, OK, now time to port to another environment, to another infrastructure, to another language possibly. Hope I don't introduce any bugs while I'm doing that. So there's a lot of other cool things that Beam has. One of the things I'm most excited about is actually we managed to fuse streaming and batch. So Beam, the name comes from an amalgamation of batch and streaming, and the fact that we eliminated about 100 other names due to trademarks and everything else. One of the things is both batch and streaming are first-class citizens, and you can actually write the same pipeline and run it in batch mode if you care about throughput and you just want to do it as cheap as possible. And then you can also take the same logic and say, OK, now I'm just going to run it in streaming mode. And you say, I'm going to read from Kafka instead of reading from, say, data files on GCS. And you can run the exact same pipeline. And there's a lot of other interesting things. For instance, the ability to create sources in composable ways. The ability to do, there's powerful windowing, data-driven windowing operations to do sessions and stuff like that in real time. And so I would encourage you all to go out if you like doing data processing. If you maybe don't like it, but you find you need to do it, go try Apache Beam. So it's on GitHub, it's open source, and this is where to go. So, of course, this is a machine learning place. So I'm going to talk now about some of the tools that we built on top of Apache Beam, kind of leveraging what Apache Beam gives us specific to machine learning. So the first one here is called Tensorflow Transform. So the idea of Tensorflow Transform is it gives you a platform to be able to do transformations, to be able to do feature extraction, feature processing in hopefully a fairly easy way. So here's the typical machine learning pipeline. So during training, you have a bunch of data, and you do some batch processing to do your data. You do some feature extraction, you maybe compute some crosses, maybe you do some filtering and stuff, and then you throw it into a neural network, and you train this neural network, or this, it might be a deep model, but it might be a wide model, it might be something more complicated. And then when you have this model to a point that you think you're happy with it, then you say, OK, now I'm going to go use this model. And so you put this model over here on your serving stack, and when requests come in, then you do the same transformations, and you feed that into the model, and you get your results out. And one of the problems here is now you've written your code twice, once during batch and once during live processing. And often these are very different systems. For instance, your live processing, it might be as part of a web server. It might actually be embedded like on a device, like a phone or a car. Very different than what you have in your data center. And this introduces the problem of training serving skew, where no matter how much you perfected your model, you've got the perfect ROC curve. It predicts things 99% of the time. But if you do the same transformations that you did when you were training your model, when you're serving, you're just not going to get your good results. No matter how good your model is, if you're feeding it bad data because you're normalizing differently, it's just not going to give you what you want. And this turns out in production, it's a really simple concept, but in production, it actually turns out to be harder than you expect. You do some tweaking, you change your batch processing, you boost your scores, and then you go and you say, OK, now I got to change my serving model, and you change it in one place, and you don't change it in the other place. And then you wonder why your predictions are off. So the idea of TensorFlow Transform is when you do your pre-processing of your data, as well as the kind of the transformed examples being an output, the transformation itself is a second output of the pipeline. And this is represented as a TensorFlow graph. And then you take this TensorFlow graph that was outputted by your transformation pipeline, you glue it onto your model, and now you have a single hermetic thing that takes raw inputs and produces the trained outputs. And you don't have to worry about this skew anymore because you can move the single thing around anywhere. And since it's a TensorFlow graph, you can execute it anywhere that you can run TensorFlow, which presumably is anywhere that you run this part here anyway. So this is the TensorFlow Transform's kind of key idea. So let's look at how to write a TensorFlow Transform pipeline. So the crux of a TensorFlow pipeline is you have this preprocessing fun. This preprocessing fun kind of defines what are you going to do to your inputs. So here we have, say I have 3 inputs, X, Y, and Z, and I'm going to do some preprocessing to get the features that will be more amenable to actually feeding into a neural net. So the first thing I do is I want to normalize. And that's this code here, TFT normalize. I'm normalizing X. And to normalize, you need to compute the mean, you compute the standard deviation over your entire data set, and then for each data point, you subtract off the mean, you divide by your standard deviation, and this is your normalized thing. And then what you can do is actually, the nice thing is, you can actually combine this transform data with other data. So here I'm going to just multiply by y, as it came in. And then I'm going to take this analysis, I'm going to run another level analysis on it, and I'm going to bucketize it. And so what bucketize here is doing under the hood is actually computing quantiles over the analyzed data, so over the normalized data, figuring out where the bucket boundaries are, applying the bucket boundaries, and spitting out discrete integers. You can also apply basically any tensor in, tensor out operation, and we have a lot of them built in. So we have like n-grams, we have things like vocab generation that they'll take a word into an int. You have stemming, you have all sorts of arithmetic operations, and all of these are available to build up your preprocessing fun. And then you return the results here as this is A, B, and C are 3 results down here. Those are our features that we're going to train on. So you notice there's kind of 2 different kinds of operations that are going on here. We call them the analyzers, and the analyzers are doing a full pass over the data. And so they're doing something like computing the sum, computing the mean, and they really have to see all the data at once. And then this is implemented as a distributed pipeline. You really need something, if your data is big enough, that can do not only processing element by element, but really do these kind of aggregations across all your data to compute these different inputs to your transformations.
So you drew the errors from just A, but are they from X, but they're also functions of Y and Z?
So they're kind of the X, Y, and Z are up there.
Right. But
Yeah.
the mean is over the X, Y, and Z, or you're referring to everything in X?
So here I normalized just X.
But X itself is a set of things.
X itself is a set of things, and I normalized X, and then I multiplied it by exactly Y. I could have also said normalized of X times Y, or something like that, yes. And you can also, flatten to get, yeah. So we here, we're computing some stats on X. We're computing some stats on the product of X and Y. Here on this side here, these are pure transformations. We don't need any stats to perform those. And then the trick is to get our TensorFlow graph. Once we've done this computation here, we can take the result of these analyses and we can plug them in as constant tensors on the right-hand side. And so now what we have on the right-hand side is something that does just transformations, and it's always one instance in, one instance out. And this is what we can apply at serving time when we just have one instance. You can feed it into the model, and it just transforms it according to the same way that we transformed it before. So what can we do with TensorFlow Transform? So with our analysis, we can do pretty much anything that we can do with a data processing system. We have access to the full data set. We can slice and dice it. We can filter it and all sorts of stuff. And then on the transformation time, we have a restriction here where we can only do things that you can do with TensorFlow. And this is so that we can embed this into the TensorFlow graph right next to the serving graph. But the thing is, you can do a lot of stuff with TensorFlow, so it's not as restrictive as you might imagine. But we can't do, for instance, full pass analysis here, because it doesn't really make sense to say, when an instance comes in, you say, well, I want to compute the average of all instances. That doesn't really make sense. You want to compute, the average of all instances that were in your training data and apply that to normalize this particular instance. So TensorFlow Transform has a bunch of built-in stuff. There's different scaling. You can scale, the min and max to -1,1. You can scale by the normalized, like I said, with the standard deviation. There's a lot of string operations or splitting on strings, computing crosses, computing n-grams. You can compute vocabs on your strings to do embeddings. You can do quantiles. Another really handy operation is you can actually, if you have a model that you've trained for something else, you can use that in your preprocessing to extract features for this new model that you want to train. And so this is really handy. For instance, if you have a generic model that, say, does image processing and gets features out of it, now you can try and use that as an input to do your processing to then do further model training. So that's TensorFlow Transform. I think I'm going to pause here. Are there any questions about TensorFlow Transform?
Do you know how compatible this kind of stuff is? Like, handles any
Yeah, so it's built on TensorFlow. Oh, yeah, I'll repeat the question. So the question was like, how compatible is it with CUDA and graphics card and that kind of thing? So pretty much it's actually using TensorFlow itself. So any accelerators that TensorFlow use, that support, so if you have a compiled against CUDA or whatever, this will use that as well. Yeah, and it actually, one of the important things we had is we do batching to sufficiently saturate the GPUs and stuff, because if you pass things one instance at a time, it just doesn't do it. So we batch these things to really take advantage of the high throughput of accelerators. Yeah. Any other questions?
So, is there a difference between the how can I mention that this is a particular training transform and this I'm doing transform the testing? Is there any evaluation mode or training mode or something?
Yeah, so typically what one does is one passes there's kind of two modes you can do. You can actually pass your entire data set through here and compute normalized on your entire data set. And then at the very end, what you do is you bifurcate. You only train on half of the transform examples, and then you evaluate on the other half. Another thing people do is they will only pass their training data set through this thing, train on that, and then they take this graph right here, pass their eval set through this part right here, and then this gives them a pristine eval to base their model quality on. So yes, you can definitely transform these things separately.
Signal processing? Is that for your transforms, that sort of thing?
I am not sure. So you can in your analyses, you can do whatever you want. So like you can call a NumPy array. So the question is is there like signal processing and stuff like that? So you can call your NumPy SciPy operations there. I don't know what kind of support TensorFlow itself has for this kind of thing. Although, depending on how you set up your environment, there is a pyfunc operation in TensorFlow that just takes a Python callable, and you could of course take this and then pass it on to NumPy or SciPy or whatever. So yeah. Okay. So this is the TensorFlow transform kind of pipeline. Well, we built this on Apache Beam, and the goal is to be able to say, well, now since it's built on Apache Beam, you can run it anywhere you want. And we're, like I said, this picture isn't quite complete, so we're still filling in some of the details here. But we're really close to being able to run it on each of these different runners that supports the portability API. So the next thing I'm going to talk about is TensorFlow model analysis. So this is kind of the other side of the gate, where you've transformed your data, you've done your training, you want to say, well, is my model really good? And so I'm sure you've all seen this curve here. It rates like how good is your model based on kind of just the very top level. And you say, well, is this enough information? If I have a second model and it comes out, the curve is slightly up and to the left, do I want to instantly deploy? And the thing is, this is kind of a top level measure of how good your model is, but it's not the end all be all. If you really want to understand your model, one of the important things is you really want to slice and dice. It's kind of like, for instance, when you're looking at a population, you can't just say, oh, well, I just know what the average is. That's good enough. You really want to segment into different populations and say, well, is it really going to be better for each different population? So lots of times when you have a model,
it's 7 o'clock.
Okay. So you'll have these different populations will act differently. So for instance, you'll have this black line. If you're living on the black line, this is a really good model for you. But sometimes maybe you have a segment of your population that's this blue line, and it's a significant regression for the people in this blue line. They might be a minority, then maybe that's why the model performs so poorly on them. But on the other hand, maybe they're a very vocal minority. Maybe they're an important minority. Maybe they're actually the minority, but the black line was really easy to predict for your machine learning setup. And so that's why it optimized for getting better predictions on the black line at the expense of the blue line here. And so what the model analysis does is that actually lets you slice and dice into your model and figure out where is your model performing well, where is your model performing poorly, before you actually go and deploy the thing. And we have this kind of nice Jupyter setup where you can actually deep dive into your model. And this also brings up another thing, which is model fairness. So as we're applying more and more machine learning to things, one of the things we have to be really careful about is that we don't kind of incorporate the biases that are already in our data and expose those to users, and possibly worse, as we apply machine learning, amplify those biases in this feedback cycle as we use more and more machine learning. And so there's this great site here, ML Fairness, that's great to check out, to kind of different things you can do to understand the problems you might have with your data and how to counterbalance those. And that's actually it's a very difficult problem, but something to think about as you're productionizing your machine learning. So back to kind of understanding how does this work? Well, what you do is you export the model that you saved, and this is a standard thing that you're going to do if you want to be able to serve. And you also export a second copy of your model that's augmented to pass the training variables through and so on. And when you do this, what we do is we do some analysis on this second model to compare them against the original model. So here's kind of an example of the Beam pipeline that does it. So we take our raw data in, and we have this operation called evaluate and write results that will evaluate your model across these different dimensions. And one of the reasons that you want to do this with big data is if you just want this simple ROC curve, what you can do is you can just sample and get a pretty good estimate. But if you really want to slice and dice, every dimension is kind of reducing your data by a constant factor. So you really have an exponential decrease in your number of data points based on the number of dimensions that you have. And so you throw in 3 or 5 or 10 dimensions. Now you really want to be processing things on your entire data set. Otherwise, your error bars are going to be so big on any individual segment of your data. So and then once you've done it, it actually spits out this Jupyter notebook that you can use to understand how evenly your model is performing, where are the places it's performing poorly that kind of might be hidden if you just look at the single ROC curve. So that is TensorFlow model analysis. Any questions on this? Yeah.
When you mentioned slicing and dicing, you mean more of a cross-validation step, or more about a feature engineering step? How is slicing the data across the rows, or it's more of column as
Yeah, so what you do is you slice your data, you define your features, and what you can do is you can slice your data across whatever features you define. So like, a common thing is like geographically slicing things according to time of day, that kind of thing. And you actually slice across features that you don't actually use for prediction if you want to. Yeah. Okay. So if you notice, I talked about 2 different components here. There's actually a paper we published at Google called TFX that explains kind of a lot of these pieces that we use to do machine learning at scale. And so here's, again, you have to imagine, there's boxes around those words. Here's a bunch of the different components. This is a simplified level, but of the different things that we use to do machine learning at Google. And these are the things that that are currently available. So the trainer, of course, let's start here. We have the TensorFlow Transform. This is what I talked about first. The trainer, of course, that's kind of the nexus of what TensorFlow started out as. The model analysis was actually just open sourced a couple months ago. And then we have TensorFlow Serving, which allows you to serve things at scale. So you load a model into memory and then kind of like have a web server that's serving this. And there's a whole bunch of other pieces that we would like to open source. So for instance, we're doing some stuff with the data ingestion algorithms and pipelines that we're trying to open source currently. We're hoping to have those out in Q3. And then as well, we want to be able to have, when you do this orchestration, if you have all these different pipelines, well, you run one and then you run the other one. Well, it's really nice to have a system such that you feed it some configuration and it automatically decides when to run the pipelines, when to validate your models. If you trust your validation enough, you can actually have it automatically push your models once they become better than the models you're currently serving out of, do A/B testing, stuff like that. And then we're hoping that eventually we can open source the entire stack. So this is something that we've had internally at Google for a couple of years, and it's reduced the amount of time that people can get up and running and productionize an actual machine learning system from, like, before it used to take months and months from the initial idea, we should do machine learning to, predict X, to actually a matter of, like, sometimes as low as weeks or a single month to go from this initial idea to plugging it into the system, and it takes care of the orchestration and all the other details. And then you can just spend your time focusing on, what features do I want to extract? What kind of what model do I want to train on? And it kind of takes care of the rest. And so our goal is to really open source all these different pieces on top of a system like Beam, so that really we can, so it makes it easy for other people to do machine learning. So.
Very good demo. So for the model evaluation, you mostly talk about how the model works on different subsets of the data. But you have a way to analyze the model in terms of which turned out to be important features and things you want to learn, like if you try to understand something from the model.
Yeah. So there's something called Tensor Board that is used a lot for that, and that you can look at it's still kind of an art more than a science when you have a model and you say, well, what was really important, but it allows you to kind of like take your model and say, okay, which features really matter, where are my predictions really coming from, understanding the flow through your model, and there's Tensor Board is really good at visualizing that. So that's not part of this, but it is definitely critical, and especially when you're iterating on this step. And lots of times going back to this step, that's a really useful tool, for sure. That's one of the simplifications. Is no, that's not one of the boxes up here.
So when you last asked me a question about the training and evaluation, or testing and evaluation, I was wondering if there is any trainable parameters in your TF transform, so I could use it separately.
Yeah, so TF Transform is actually a library, and it's a library of transformations that you can put together any way you want. So you can say, read this data, then send it through this transformation, and then write your results out here. So you can wire it together in a bunch of different ways. In fact, lots of times what you do is you say, read the data, partition the data, do the transformation, then apply that transformation to the second partition, and then write the results out this way. Is a common way to do it. So you can actually, partition your data randomly and as part of your training.
In the transform itself, are there any trainable parameters that I could train with my network?
In the transform, you mean in the model itself?
In the transform itself, some transform. Can I train any parameters in the transform?
You can't. So there's some speculative work that we're doing to move that boundary. Right now, the transformation is fully complete before you start your training. Other than like where I said you can plug a model into it. But we're actually there's some investigations, and mostly it's an API question of how do you blur that boundary so you can have trainable variables in the transformation, because that is definitely a lot more powerful.
That will increase my network moving the transform.
Yeah. But right now it's not that way. Mostly it's because of an API, drawing the lines and making that work well is one of the things that with this is, and actually Apache Beam before it is having something that is comprehensible and easy to use and understand and importantly evolve is sometimes more important than having something that's powerful. And of course the holy grail is where you have something that's easy to use and can then become something powerful the more you get to know it. And so that's why we're very careful with how we choose our APIs. So yes.
I'm thinking about, there are things that are to encourage it's easy to overtrain. And you're talking about that iteration of the training and evaluation and going back. It's really important, right, when you make all kinds of decisions about your model, and you can't get a good estimation of how well it performed if you don't have a validation set aside that you vow not to change the model after you try with it. Otherwise, it kind of learns that. So the question is, do you have ways of encouraging good practices in that respect? Like something that as you iterate, pulls more of the data, but always encourages you? Or are you thinking about these things at all?
It's usually more by convention than we actually enforce it. So the configurations actually will split stuff out into your training and your eval set. and then they will give you the results of your eval. And lots of times what happens is we actually, on this right here, we will automate it. So we will just, it's kind of like a yes, no. Are you going to push or not? Did your model get better? And there you don't actually, if your model got worse, you kind of go back to the drawing board, but you really don't want to like look at your eval data set. Because like if you do something like, if you really say, well, why did it get worse?
But you look at how well it did on another data.
You do.
Like, I think, so one way you probably should be doing it is after you do yes and you decide to push, have data that it only sees then, because that's going to give you the most honest estimate of the actual performance.
The other thing that I would say kind of helps us, at least for most of the applications that we do, is your true evaluation is your future data. So this is actually a cycle. And what happens is, you haven't seen the future yet. And so, you go through the set and you have a model. And then what you're really doing is you log how well it performs on future data compared to, how well the old model might have performed. And that's a powerful way not to cheat. So, and certainly there's, a lot of applications you can't do that with. At least a lot of the teams that I work with, they're, continuous systems. So, yeah. Okay, and I actually don't know how much time I have left.
So just
TensorFlow Transform. The TensorFlow Transform, excuse me, can feed into a data flow runtime. My question is, where does the Cloud ML engine fit into this? I know it provides training and serving.
Yeah, so the Cloud ML engine is actually, at least in the current form, mostly focuses on this training. So it says, once you've transformed your data, and I don't care how you transformed it, then distribute the training part. And that's where the Cloud ML engine mostly fits in. And then the TF transform is actually developed by some of the people that were on the Cloud ML team and kind of, bifurcated the products to make it well-defined. But yes. So they complement each other, I would say.
When you had that two parts of the graph, right? The batch processing to do the transformed data, and on the right side, which I assumed was the evaluation part. Can that also be used for the serving the model? Yeah, so you actually plug that into your server. If I have so when you do serving, what you do is you take that output, you actually can glue it right onto your serving model, and then serve that hermetic component at serving time and push it out to wherever you want. Yeah, that's one of the goals. Okay, I think unless there's any more questions, I think we're good.
thank you for the great talk. I'm personally going to watch it again. Let's see. Everything is online, so if you want to watch again, then it's going to be on the YouTube channel. Okay, my name is Eila. I usually don't come up to the stage, but I'm the meetup organizer. And this time I'm going to share with you some experience I had using Google machine learning for personalized medicine. So you'll see some of the things that Robert showed and some others perspectives. I'm going to introduce a little bit what is OrielResearch is doing, what the question that is being asked, how the data processing is being done, and the model training. This is only one way to do things. Things are changing and evolving all the time, and there are many, many other ways that can be used, and you can suggest also different ideas. So just a little bit about what is precision medicine, what the promise and the challenges with precision medicine. So we have this patient with melanoma lesions on his body, basically very advanced obviously very advanced melanoma. He was tried on a standard disease. Actually, this is a patient from Dana-Farber here, Boston. Immunotherapy that didn't work. And then there was one idea to check him. It was at the time of a clinical trial on mutation in a BRAF gene, and he was found to be positive. So say, why not try giving him a BRAF inhibitor, basically a very selective drug that inhibits this mutation. And he was showing a great response, that you see on the right. This is an amazing example. Bad news about this patient that he relapsed after a while and tried on another precision medicine. But obviously, you can see how well when we choose the right precision medicine, how good it could be to the patient, how much toxicity it's saving him, no chemotherapy, basically a pill that is being taken. The challenge with precision medicine is knowing who is going to benefit from this drug. Even if he has this BRAF mutation, it doesn't promise us a response for patients, and there is no really certain way right now to select patients based on response. And how big is this problem? So it's known right now that about 12 million patients are misdiagnosed in the US every year. In this case, like this melanoma patient, he's not misdiagnosed, but based on his diagnostic, there is no good way, decisive way to know what is going to help him. Of course, this is saving money for the insurance companies, a good incentive to do machine learning for them, a lot of toxicity to the patient, frustration, and toxicity as that. The thing is that patient with non-diseases like melanoma is considered to be good diagnostic of the patient, or the correct diagnostic of the patient. But actually, this is another misdiagnosed in the OrielResearch view, because the fact that we gave it a name doesn't give us a good medicine that we can prescribe to the patient or going to be beneficial to him. So yeah, there is an issue with the black here. I'm sorry. But here I'm showing the diagnostic as it's being right now at the clinic. So each circle here is a disease. And there are patients from this is triangle patient for lung cancer, squares for leopard syndrome, which is another skin disease, and this is for melanoma, who is a skin cancer. We are grouped there based on the patient symptoms, based on clinical data, based on imaging, based on PET-CT, many other tools that the doctors have right now to diagnose patients. But we suggest that if we look at the diagnostic features of this patient, we might find another classification of the patient, another diagnostics. And if we even add the response to therapy, we might be able to prescribe the right drug to the right person, to the right patient. And then by machine learning classifier, we're getting to 4 different diseases that are sharing the same common genomic properties, and also are gonna probably respond to therapy the same way. So OrielResearch mission is to diagnose diseases and recommend matching therapies using machine learning models. This is about that. So how do we do it in practice, in real life? There are 3 stages. One is the data. The other one is the model training. And the last one is the serving. I'm not going to talk about the serving right now, but I am going to look about development with perspective of a company that consider cost and one short pipeline to drive to results. So when this is a OrielResearch experience, but basically could be implemented to any other question in other applications. So we ask, the data is publicly available. This is going to save you money, of course, on the storage of the data. Genomic data, a lot of genomic data is publicly available, and there's a huge movement to share more and more data. What kind of storage type do you need? So this could be, you can consider if it make a decision based on the data type, if it's structured or unstructured. There are BigQuery, Bigtable, SQL, many options that I'm not going to talk about deeply now, but basically this is things that you want to ask yourself. What is the data size? How often you're going to access it? This is affecting your cost. Is it going to be a live or offline data? Batch, bound, unbound data? This is a question you want to ask yourself. And what is the pre-processing that you're planning to do? Is it going to be a format, labeling the data, and etc.? And with the model, there are two ways to generate a model, or at least two main ways. One of them is transfer learning, and the other one is developing the model from scratch. Huge impact on your cost and on your time to market. And of course, like Robert said, all the time there are new tools coming up, saving you weeks of work and coding, and just being alert to them is going to help you dramatically reduce your costs. So when OrielResearch is pre-processing genomic data, we're using Apache Beam, Data Lab, which is Google Jupyter. Dataflow is our runner. BigQuery, data storage. Google Storage, also blob of storage. Stackdriver is the logging environment that Google is offering, which is awesome. And the way we're saving the cost is using a small set of data with the finite storage type, as Robert just said. You can do your unit testing or something like that, and then running the full pipeline, including the training and everything, and then scaling up before using all the mass data that you have. Using local runner, these have some benefits in reducing your execution time. You'll have to have a bigger machine when you're using on a local runner, and you pay for execution on a bigger machine, but then you debug faster and move to Dataflow runner, Flink, Apache, whatever you want. And there again, you have some debugging phase that you don't see in, that's my experience on a local runner, but it's not something, it's unresolvable, it's not something major. Okay, so I'll show you some data processing demo. It's hard to show live demo on a Dataflow because there is some time that of ramp up of the machine, a few minutes of running before execution. On local runner, it's easy, but basically this was specific example was taken from the Google tutorials. I'll scan it fast for people who are not familiar with Beam. Basically, it's a pipeline. It's a Python code where we declare the pipeline that we are going to use. The lines is an object that they call it the peak collection, not really important, but basically this is reading the data that you want to process and making an object from each line in the data, each sample, each whatever you are processing. Based on that, this example is counting words, how many times each word is presenting the text, and then each pipe here is working on one line. So basically, you'll have one read the text, extract the words for each line, pair it with one, each word is going to get one, and then group it by the key, which is the word, and map it, sum it, based on the keys, sum the ones that you have next to each word, format the data, and write it to text. All this is going to build a graph that you're going to run and then wait until finish. If you do it on a local runner, it's going to happen on a machine. If you do it on the cloud, it's going to run on your cloud execution. So there is a way to see this kind of process. It's called data flow visualization. This specific one is not the one that you see here. Here you will see 7 steps that are happening. Here you see something that was running on genomic data. For each sample, there were two actions that were happening. Total of three actions for each line in the case of word counting. This is very helpful. From here, you can go into the logs and see exactly what's going on. When developing a model, as I see the 2 major options that I have is developing a model from scratch, or use a pre-trained model and enforce your data on this pre-trained model. The way that to use it, the TF Hub, I think also probably with Transform there is an option to do that. using data flow, Apache Beam ML, and Stack driver. Again, using low volume of data will save you money. Using transform model training going to save you money. Just in a nutshell, what does it mean? There is, for example, pre-training model of image recognition. I saw someone who was doing audio data that he transferred to pictures, audio data, and then feed it to the pre-trained model, trained his model and got output. This is usually a very short process when you leverage on all the information and all the millions of samples that already were generated with the pre-trained models. So if you can take something from NLP, from image processing, from any other model and use it to train your model, you're going to save you a lot of time, execution, and money. Example of how it happened, how it's working on TF Hub. So basically, Hub is a library of many, many models that were already generated here by Google, but basically every company can upload their model. You can, in this example here, they're using string mapping, a map array of string to embedding, like you do in NLP. You can do it in many other ways as well. I can show you what does it mean. So basically, if you take this piece here, this is the link that you're going to import the model from. When you put it on your browser, you're actually going to see it. So I see it very small here, but basically, will tell you how to embed this piece of code. You can embed the models with, let me see, ImageNet, for example. You can embed any of the versions. You can take the classifier to train on top of it. And you can take also the features if you want to run the model easily on data that you want to classify. So you can try either the classification or the feature vector. So if you put it in the code, it's going to import. If you put it on your browser, you're going to see the right way to import it. And then just straightforward, you're going to use it with your new data and run it, and it saves you a lot of code and development time. And if you have any question, please ask me now. If not, I'll give another 2 slides about genomics. Yeah.
Question. Use the Roberts, but use the back end. So separate voices,
Robert, you can take this. It's definitely a question for you.
So you decide the backend just based on what your preferences are. If you're a Spark expert, I don't use that. I noticed you're using Dataflow, which is basically it's a suite of service offered by Google where you don't have to manage the servers. You give it a description and it manages all the servers for you. So yeah. The idea is you should be able to switch between backends easily. Then you choose the one that's your needs best. Is there any extra setting? Depends on how different runners require different levels of tweak. Yeah. So with Dataflow, our goal is to have no knob solution. Other runners, especially newer runners, more primitive, you have to set everything. So yeah.
My specific decision on Dataflow is I was new to the machine learning on a cloud environment. I just wanted something that worked fast and quickly for me. So that's it. I can give you a little bit about what is the genomics, the complexity of genomics that is being used, right? Why is it difficult to bridge this gap with the big data? So it's really going to be very, very basic what I'm going to show. So we have the cell, and inside the cell there is a kernel called the nucleus, and inside it there are the chromosomes. And each chromosome is, when you stretch it out, is going to be the DNA. And the DNA right now is it is a set of 4 letters. Not going to change anytime soon. And this is the set of letters that we see here. There is a transcription. For people from computer science, I would say this is the code that is going to be run. There is some there is some if and for loops and stuff like that that will bring you to the transcription, and the protein is going to be the execution that you're going to run in the cell. So basically, there are more than one type of data that is being sampled from the cell. It's the DNA that is a set of these 4 letters, a long set of, and then there is the RNA that shows us what was actually expressed in the cell from this code, what actually was running, and the protein is what was built from this kind of information. This is a quantitative information. This is also quantitative information with some sequencing data, and this is the sequencing data of the DNA. Mutation, what does it mean? From this set or a long series of information of the DNA or RNA, something was broken, something was changed. Usually the neighbor across the street is going to be changed as well as a result of one change. And then different protein is going to be generated, and the functionality of the cell is going to be affected. Sometimes it's meaningful, sometimes it's not. Sometimes it's meaningful, like with this patient with BRAF in a specific context when other things are presented in the cell, and sometimes things that looks harmful on one patient is not harmful on other patient. That makes it difficult to look at the big picture, and understand what is coexistence is making someone sick. And that's it.
So from the types of data that you showed there, what is the type that you process in OrielResearch?
So right now we're processing RNA data.
Are you using any of the transformation tools that?
Yes, we are, but not with the file transfer. We are using Apache Beam to transform the data, but not with the TF transform, and not with the analyzer that I'm doing right now, which is normalizing data and stuff like that, which I'm not using right now.
So, did you do the feature selection?
So the feature selection is gonna be from the RNA. We're using a method when we can use the other pre-trained models to use this model. So the feature selection is done by the pre-trained model. Yeah. If you are using image classifier? No. Yeah.
Just to follow up with that question, I'd only heard of transfer learning. You could say more about that.
So basically, it's the way you decide to present your data. If you find a good way to take your data, I don't know what you're working about, this specific one, I can send you also, I think it's available on YouTube. You know what? Go back to Google with genomics. They develop a deep variant, which is basically mutation calling. If something is this, mutation calling is actually detecting mutations from sequence data. And the way that they were doing it, they were using IGV, which is editor. Let me show you. This is the editor for mutations. And this is how the evidence that you see here for mutation. In every read from sequence, there is a sequence of data along ACT that I showed you. So they read many lines here. Each one is a read. And if you see enough evidence for mutation, you call it a mutation. And you need some kind of threshold of evidence. So at the deep variant, they decided to take these pictures, which is genomic information, and capture it and label it to what is mutation and what is not. And then here you can do also augmented data. You can generate data by yourself and use the image classifier for that. So you have to be creative about that, but transfer learning is definitely, in my way, the way to go, in my view. Okay, guys. So thank you, Robert. Thank you, Grace. Coming all the way from California. Also, Robert. Noam just told me on the side, what a nice group is the Apache Beam. And I said, I felt the same when I came to you guys. and hope we have a lot of collaboration work-wise, development-wise, and also with meetups.